I guess we can start now. So welcome everybody to our seminar. Today we have Stephan Rasp. He did his PhD in Munich at the Meteorological Institute, if I'm not mistaken. And right now he is a senior data scientist at Climate AI. And he's going to talk about online training of neural networks embedded in climate models. So Stephan, the floor is all yours.
Yeah, well, thanks very much for having me, and thanks for tuning in. So I'll talk about the basic concept is essentially how to combine machine learning and physical modeling. And this is going to be, in this case, in the context of climate modeling. And so we're going to talk about some of the challenges with this approach and potential solutions. And so we're going to I think like a lot of you will already know the basics of machine learning, but maybe not everyone has a background in climate science. And so I just want to start off with sort of explaining what are the problems, what are the key issues that we're dealing with in climate science, and why are we motivated to take a machine learning approach. So if we think about, what is it essentially that we want to know from climate modeling, it's, how will our planet respond to an increase in greenhouse gases. And so a key quantity is, how much warmer will it get as we emit more CO2 and other gases. And so this is, of course, really important because we want to build good policies based on that. Now, in 1979, the first organized climate assessment was done, and they estimated how much warmer the planet will get as a response to a doubling of CO2. So if you just do the thought experiment, or you do this experiment in a climate model where you just from one moment to the next, you increase the amount of CO2 by 100%, and then you let the Earth reach a new equilibrium state, then how much warmer will global mean surface temperatures get? And so they estimated this, this equilibrium climate sensitivity is what this quantity is called, to be around 3 degrees with a probable error of plus minus 1.5 degrees. And if you think about it, this like 3-degree error span, that's quite a lot, because inversely, this gives you a lot of uncertainty about how much more greenhouse gases can we emit before we reach a certain threshold, for example, the 2-degree goal. So this was 40 years ago. Let's fast forward to now. And so let's look at what current climate models say about this. So each of these dots is a state-of-the-art climate model. And on the y-axis, we can see this quantity, the amount of warming you get in the response to a doubling of CO2, the equilibrium climate sensitivity. And you can see that it ranges from around 2 degrees to almost up to 5 degrees. So we still have this around 3-degree errors, uncertainty span. And this is kind of shocking because, of course, the models are a lot more sophisticated. They're a lot more computationally expensive than the models that we had 40 years ago. So a key question is then, why do we still have this uncertainty? And people have, of course, looked at this. And one simple way to look at it is what's shown here in this scatter plot. So here on the x-axis, what's shown is what they call the low cloud reflectance change. So this is essentially, low clouds are these big sheets of clouds that you see when if you've ever flown across the Atlantic or the Pacific, you'll look out of the window, you see these like big fields of clouds, and they're really important for the climate because they do not contribute a lot to the greenhouse effect, but they reflect solar radiation. So in effect, they are cooling the planet. And so what's really crucial to find out then is, as our globe warms, will there be more of these clouds? And that would be, of course, a negative feedback effect. Or will there be fewer of these clouds, and that would be a positive feedback effect? And as you can see here, this is essentially what's shown here. There's no certainty about the sign and the magnitude of this effect. And there are other studies too that basically point towards the representation of clouds in climate models as the main contributor to uncertainty in climate projections. Okay, so why is it so hard to represent clouds in climate models? So if we think about how a climate model works, in essence, you are looking at the atmosphere and also the ocean and then also the land, and you discretize, let's just think about the atmosphere, into cubes, and you solve the equations of motion, of the air, of the ocean. You solve this on this discretized grid. And of course, the grid spacing, so how fine your resolution of this grid can be, is limited by how much computing power you have. So you're almost limited, and currently climate models have a grid spacing of around 50 to 100 kilometers. So it means like a horizontal grid box is around 50 to 100 kilometers for one edge. Now, if we look at a picture of some clouds, it's just a random picture of some tropical convection, we draw sort of an arbitrary 100-kilometer box in there, then we see that a lot happens below this grid scale. A lot happens within this box. So we see that all of these small, shallow clouds that we've learned are so important are much smaller. Even these big clouds that are transporting a lot of heat around, they're smaller than 100 kilometers. And then you can also see now the way radiation, the way solar radiation, and also you could imagine infrared radiation interacts with these clouds. All of this happens on much, much smaller length scales. So this is kind of a problem because all of these processes that are really important for the climate, they cannot actually be represented on the model grid. So what do? What we need to do is essentially we need to come up with simplified descriptions, with approximations, what effect these subgrid processes have on the resolved scales. These approximations are called parametrizations. And the typical way of developing these parametrizations is to say, okay, well, based on physical intuition, based on looking at observations and maybe high resolution modeling studies, we come up with a simplified model of the process that we're interested in, for example, clouds. We write down a simplified description, simplified equations. These will have a handful of tuning parameters, and these tuning parameters we then tune manually to give us, good climate forecasts or weather forecasts. And it's basically the same process in weather forecasting. And so a climate or weather model, essentially, if we look at what happens in a single time step of such a model, then is what we call in climate modeling the dynamics. So this is the basically solving the Navier-Stokes equations on the grid. And then the physics, and the physics is everything that happens below the grid scale. So these are these parametrizations, these approximations of the processes that we cannot actually represent on a model grid. And so in the time step, you first do dynamics or physics, it doesn't really matter, and these two interact with each other. And if we just look at these subgrid approximations, they look at the state of the atmosphere at a given point, and they then make an approximation of the effect of these subgrid processes, be it clouds, be it radiation, on the model grid. And so you go round and round like this. Now, as we've seen before, if we look at the uncertainties of climate models, we can pinpoint the main cause of these uncertainties to these approximations, what we call the physics here, and particularly the approximations of the subgrid clouds. So we just kind of want to do better with that. And of course, we can develop more sophisticated approximations, and we are doing this. But while they might become more realistic, more sophisticated, it doesn't seem to really decrease the uncertainty in some of the key things that we're interested in, like how much warmer will it get as CO2 increases. So maybe we want to think about a different way. And of course, ideally, one way we can do it is just say, let's just resolve the clouds. Let's just run a model where the grid spacing is so small that the clouds are actually on the grid scale, and we can resolve them. And we can now run global models that do this. So this is an example of a model. This is from the ECMWF model that's run at 1.4 kilometer resolution, at which point you can get most of the bigger clouds in the model. And we can run these simulations now, and you can see this is a snapshot of such a simulation. On the right, you have the corresponding satellite observations. You can see, they match really well, and you can see all of these like really detailed clouds that you would never get with a climate model that has 50 or 100 kilometer grid spacing. And there's also research that shows that these models represent observations a lot better than the coarser, lower resolution models. Now, of course, the problem is these models are really expensive to run, and so we cannot run them for long enough to actually estimate climate change projections, where we need to run many models over 100 years or more. So we can think, okay, well, how long is it going to take us to get there? And this is shown in this kind of really interesting graph. So this is as a function of time. First, in blue, you can see the computing power. So this is always the latest supercomputer, and you can see that computing power measured in flops here is increasing still according to Moore's law, and let's just assume this is going to continue like this. And then in the orange circles and diamonds, you can see this is the horizontal resolution of climate models. And you can see actually that it doesn't quite increase as quickly as computing power. So it doesn't scale the same because we're not only increasing resolution, we're also adding complexity to the models. So in the 1980s, climate models were just representing the atmosphere. Now you get these Earth system models that represent the ocean, that represent the land, chemistry, and so forth. So we're adding more complexity as well. And so, of course, the resolution does not scale quite as quickly as the computing performance. But even if we assume that it does, and we know that to represent clouds, we need to go below 1 kilometer, then we end up somewhere over here in 2040, so 20 years from now. And of course, waiting that long is probably not what we want to do. So we want to think about, can we develop a shortcut that gets us there faster? Because of course, while we cannot run simulations for long enough with resolved clouds, we can run short simulations for weeks, months, maybe a few years soon. And can we somehow utilize those to improve our coarser climate models? And the idea here is to use machine learning to do this. So again, if we think about sort of what happens in a model time step, you have the dynamics, and we know that this is quite good and we don't want to really mess with it. And then we have the physics, so all of the subgrid approximations, and we know that these are kind of uncertain. They're really hard to build. And so the idea is, well, can we replace these traditional physics parameterizations with a machine learning model? And so to do this, if we think about what goes into the parameterizations, it's the state of the atmosphere at a given point, what comes out of the tendencies. We need to build a training data set of state and tendencies from our high resolution simulation. So the basic gist of it goes like this. You run a short-term high resolution simulation. You apply a coarse graining, and from this coarse grained state, you also figure out what are the coarse grained tendencies. You build this training data set, then you train a machine learning model to do the mapping from state to tendencies, and then you plug your machine learning model back into your climate model instead of the traditional parameterizations and run it in a climate or weather simulation. Now, it turns out that actually this coarse graining step, figuring out what is the state and the subgrid tendencies, is not that trivial. But for the sake of time, I will not go into it. Rather, what I'll do is I'll list sort of the different approaches here. If you go to my website, I uploaded the slides for this presentation, so you can look at them later if you want to look at these references. There are different approaches. All of them have their advantages and drawbacks. So if you're interested in this, you can check out these papers. They all represent different approaches of doing so. Now, let's assume we've solved this step of building this training data set. We've trained our model, and then we plug it back in the climate model. There are a bunch of studies, notably those 4 here, that have done so. And let's now look at the results. And we're going to run through the results pretty quickly, because rather than going into detail about how this works and what works and what the difference of these approaches is, I want to highlight some common themes that emerge from these studies. So this is the first paper. And of course, if you train a model to simulate high resolution simulation, then the best you can get is you can exactly match the high resolution simulation. So what's shown here now? So this is a study that we did. And essentially, we ran a high resolution simulation in an aquaplanet setup. So that's a planet without any continents, just to simplify the problem. And on the left, you can see this is the heating caused by the subgrid clouds. And this is latitude, so this is the South Pole, North Pole here, and this is height. And you can see that you get this big heating spike here at the equator, where you get all of these tall cumulonimbus clouds. And of course, the best that the neural network version of the model can do is it can basically match this, and it does so pretty well. This is a traditional parameterization, and you can see it looks different, but this is also not the best parameterization, one has to be honest about it. So then the resulting temperature state, so one thing that we're really interested in climate modeling is the mean state represented. And you can see this is the difference to the high resolution from our neural network version. And you can see that we have differences below 1 Kelvin for most of the tropospheres at the lower 10 kilometers. But there are some biases in the stratosphere. And so while these results are, kind of encouraging, we do have these biases, and we have to think about how would we get rid of them. And we'll keep this in the back of our minds because we're going to talk about it later. Now, this is something pretty specific. So if you're not into climate modeling, you probably have never seen this before. So one thing that's really important, so the atmosphere has certain waves going on, and particularly in the tropics, there are different modes of waves, and it's often these are very hard to represent for climate models. So this is a space-time spectrum of tropical waves, and you can see we have some Kelvin waves here. This is the Madden-Julian oscillation, which is another oscillation that's really hard to represent often for climate models. And we can see that the neural network version does so pretty well. So this is encouraging. Something that's a little bit more just graphic here. So this is from a different study, similar setup. And they have the high resolution simulation here, again, on an aqua planet. This is why this doesn't look particularly realistic, but let's just assume that the high resolution is what we want. You can see that you have these two bands of water vapor, column water vapor is what's shown here. And then if you run this same model at a coarser resolution, it does not look like this. So that's not what you want. But they then trained a random forest. We trained a neural network. They trained a random forest to correct or to represent these processes that are not resolved in the coarser resolution simulation. And you can see that, again, you sort of recover the structure of these tropical water vapor bands from the high resolution simulation. So again, this is kind of an interesting and encouraging result. This paper, again, has a slightly different setup. Actually, they learn a correction term rather than completely replacing the model physics, but the basic setup is the same. And what's cool here is they actually tested their simulation in a weather forecasting mode, so where you start with the same initial conditions and you see how your error grows, and you can see that their machine learning corrected version in red here has a lower error than their baseline version. And so that's pretty cool. This is also the only study that actually uses a realistic planet rather than an aqua planet. But still, this is run at very coarse resolution of 200 kilometers. Now, as we've already seen with the study that we did, when they then run their model in climate simulation, like for a long term, and then they compare like the mean state biases, they get really large biases in the temperature, for example. So again, you have these biases, and you need to think about how would you get rid of them. Now, it can get even worse than biases. This is again from the model version that we used. This is the globe here, and this is sort of the heating that's produced by the neural network. And as we run this simulation, we can see it. If you look here, we can see that you get some really crazy heating tendencies, and eventually the model blows up. So what happens here is that you plug your neural network back into your climate model, and it develops an unstable feedback loop that eventually causes the model to crash. And even if it doesn't crash, this is from another study. And on the bottom here, you see a simulation with a neural network. And this is a diagram where you can see time on the x-axis. And you can see that this is the precipitation. And you can see the precipitation sort of dies out. So you have a drift in the mean state. You lose precipitation, you lose energy, essentially. So again, this is a common problem. So what I wanted to highlight by showing some of these results in not a lot of detail is essentially that, this approach kind of works. We have seen some encouraging results, which is really cool, but then there are some issues, and particularly we run these simulations and we have biases. We run these simulations, sometimes they're unstable, or sometimes we get a drift where energy is not conserved essentially. And now the question is, of course, how do we fix these problems? And so in the next slide, I'm going to make sort of the main point of my talk here, and that is that currently we do not have a great physically or scientifically principled way of fixing these issues with the methodologies that we're currently using. And I call this problem the optimization dichotomy. So a dichotomy is a really strong contrast between two things. So what is this contrast? So if we go back about, what are we actually having our machine learning models learn? It's a mapping within one time step from state to tendencies from a training data set that we've built. Now, if we think about what do we actually want? Well, we want better weather or climate forecasts, right? So a better weather forecast would be a simulation that after a few days, for example, has a lower error. Or a better climate forecast is a forecast that's run over a long time, and the sort of mean statistics, the mean state, the variability, all of these statistics match observations better than a traditional model. And so I think the crucial point here is that there's a long way between what we optimize for and what we actually want. And in particular, what's in between are thousands, if not millions, of time steps in which your machine learning model now interacts with the other model components, your traditional dynamic solver, other physical components of the model, and it interacts with itself through many, many time steps, which it has never done during training, right? And simply hoping that a model that does well on this very isolated task also gives you a long way down the road better weather and climate forecasts, well, evidence has shown that this is not always the case. Now, it's actually interesting to consider, an analogy to traditionally designed parameterizations, because it kind of is the same way. You design a parameterization, then you plug it into your climate model, you run it, and then it probably at first doesn't do what you want it to do. But the big difference is that with a traditional parameterization, it's based on physical principles. You have some physically meaningful tuning parameters, and you know from experience that if you tune a particular parameter, that will have this effect on the climate model. And so, based on physical intuition and experience, you can tune these parameters to basically match what you want. You lower the error in the weather forecast or better match climate observations. Now, you cannot do this with machine learning models. The neural network that we had in our study had 500,000 parameters. They're all physically meaningless. You cannot just start tuning those. And so we currently do not have a great way of tuning machine learning models to actually do well on what we want them to do well on. And so this is sort of, I think, the crucial problem that we have in this research area. And so, of course, we want to think about okay, what are potential ways forward? And I want to talk about a bunch of those now. Now, I'll say right away, I don't have a great answer, but these are just some things to think about. And the first thing is online learning. Now, if we think about what we've done so far, just to recap, we create a training data set from high resolution simulation. Then we use this training data set to learn our machine learning model offline. So it's decoupled from this interaction with the other components of the model. So we only train offline. And then we take our trained model and plug it back in to our climate model, or of course, this can be any other, this doesn't have to be a climate model, this can be any other physical simulation. And we hope it does well. And maybe sometimes it does, but maybe sometimes it does not. Now, the idea of coupled online learning is that essentially this is not where training stops. This is just sort of a first training step, but then you continue learning as you are coupled to your other physics simulation. So basically, as you run your real simulation, you continue learning, and you do so by running a high resolution model in parallel, keeping the two simulations coupled through a nudging term, and then every time step basically looking at the difference between the high resolution simulation and your hybrid simulation, and getting a loss from there, so that hopefully you can learn online. You can update the, let's say it's a neural network, you can update your neural network always to do better and better and come closer and closer to the high resolution simulation. So this is sort of the general overview. Now you need to think about, like, how do you actually set up this problem? And so I'm going to try to explain it in the next 2 slides. Because I don't want to take half an hour to explain it, maybe you're still confused afterwards, and so please ask me questions, or you can also, of course, look at the original paper where it's described in a lot of detail. But I'll try my best to tell you now in the next few minutes how this approach actually works if you get down to it. Okay, so for this, we're going to look at a diagram like this, where we have time on the x-axis, and on the y-axis, it could be the state of a variable like temperature at a particular point, or you could also imagine this being a point in phase space of the model. And then you have 2 models. You have your hybrid machine learning physics model, and you have your high resolution model. And this, for up to this dashed line here, is a 1 time step with the lower resolution hybrid model. That's the one in blue. And so let's think through what happens in 1 time step of this lower resolution model. So if you start here, the first thing that happens is all the non-machine learning parts of the model. So this is maybe your dynamics, you maybe a Stokes solver in your climate model, and maybe you have other model components, model physics, parameterizations that aren't represented in your machine learning model. And so that happens first, and you end up down here somewhere. And then you have your machine learning component, and that's already been pre-trained on this offline data set. And so then you run your machine learning physics package, and you add the tendencies to get to here. Now, you have another model, and that's your high resolution model, and you start it at the same point here. And your high resolution model typically will have a smaller time step. So this line actually is many, many time steps with the high resolution model. The high resolution model, it just does what it does, and then you end up down here. And of course, in an ideal world where your low resolution model and your machine learning hybrid model would be a perfect representation of your high resolution simulation, you would end up at the same point, but they probably don't. And so what you can do now is you can basically check this difference and learn after 1 time step to make this difference smaller. So ideally, you would have gotten with your machine learning physics from here to here. What actually happened is you went from here to here. And so the difference between these two is one you want to minimize. So you minimize the RMSE error between those two. And you do a little bit of maybe a gradient descent step in this direction. And that's the basic idea. Now, the problem is, now you're at this point and you want to start your next time step. But now, of course, these models aren't at the same state anymore. And if you just let them run freely, they'll eventually diverge because we're dealing with a chaotic system and so forth. And what you learn will be totally meaningless. So you need to somehow keep these 2 simulations coupled together. And so this is what's explained here. So now we start, but now we start with a difference already. Now we assume that this difference is small, so that we can still sort of assume that they're in the big phase space that we're looking at, this is still basically the same, but it will not be exactly the same. And so now we need to keep these simulations sort of together. And we do this by introducing a nudging term in the high resolution simulation. Why not in a low resolution simulation? Because this is the simulation that we actually want in the end, right? In the end, after this online training is done, we want to use this hybrid machine learning physics model to run climate simulations or something like that. So we want to keep this untouched, but we still wanted to learn from the high resolution simulation. So what you do is you introduce a nudging term that keeps the high resolution simulation close to the state of the low resolution simulation. And you do this by introducing a nudging with a nudging time scale. And then you basically, and here is where I'm gonna not go into too much detail because it would just take too long to explain. But you can basically figure out with some assumptions, like for example, that within these short time steps, this is a linear addition, which is of course not because it's a nonlinear model. But essentially, you keep figuring out, what is the loss here? What is your new ground truth during this online simulation? And you keep these two simulations coupled. And ideally, over time, your machine learning model will get better and better, and it will get closer and closer to the high resolution simulation. The idea, of course, also being that if you have biases in the coupled simulation, then this will show up here and your machine learning model will be punished for it. Similar with these unstable feedback loops. Of course, if something like that happens, your machine learning tendency will go completely crazy and they'll get a huge error. So your neural network will essentially learn not to do that. And so forth. So this is the basic concept. And as I said, I went a little bit vague here because I don't want to spend too much time explaining this. But this is the basic concept. Now, does it work? Well, it does in a simplified setup. So I'm not sure if you're familiar with this model. This is the Lorenz 96 model. So Edward Lorenz, often regarded as one of the founding fathers of chaos theory with his famous 1963 three-level model, the butterfly model. He came up with another model in 1996. It's a two-level model where you have basically a ring, and this is this blue simulation, and maybe I can try to run this again. So you have a ring of a variable called x, and there's some advection going on, some diffusion, there's a forcing term. And then you have another variable that's much smaller in scale, and that's the orange variable that also has an advection and diffusion term, but it's much faster. And these two are coupled in both ways. And you can see how they interact with each other. And the idea, this is a very popular model for parameterization research, because the idea basically being that you want to parameterize, you want to basically say, okay, my y, my fast variable is unresolved, and I need to find a approximate parameterization for this fast variable. And so I basically use this to test out this coupled online learning, and it does work quite well. So I started off with a pre-trained model that was trained on a slightly wrong data set, and then you can see during this coupled online learning, the neural network eventually gets closer and closer to the true solution to this parameterization problem. Now, the Lorenz 96 model, while it's great to test out approaches, is really easy, and sort of everything works in the Lorenz 96 model. So it doesn't actually exhibit any of the problems why we're doing this approach in the first place. Testing it in a real climate model, it would be a real technical challenge, and that's why we haven't done it yet. Now, thinking about what's good about coupled online learning is that we kind of have everything to make this work. Like, it's a technical challenge, but basically it requires coupling two models together, but it's totally doable. But there are also several assumptions that this method relies on, and that's the first is this nudging term that you introduce. you can't nudge the high resolution model too much, because then you basically will throw it off its attractor the entire time. It'll do completely crazy things or crash. But if you nudge too little, then your simulations won't be coupled closely enough, and you might not actually learn what you want to learn. So there's a trade-off here. There's a linearity assumption with adding the nudging term that might not be perfectly true. And you, of course, assume that your neural network will have essentially converged to the true solution and not just wobble around the real solution. So this is another thing that I don't know if this would actually happen in a climate model. And then there's one basic problem with basically most of these approaches that we've seen so far, and that is, well, the best we can do, even if these approaches work perfectly, is we can represent a high-resolution model. And now, while there is evidence that these high-resolution models do better than the lower-resolution models, they still have biases, they still have, errors. And what we actually want is we want to get closer to observations, not a high-resolution model. And you cannot do this with this approach because it relies on the high resolution to create your training data. Now, what are some approaches that would solve this problem? And so I'm going to present two here, basically one gradient-based approach and one non-gradient-based approach. Now, differentiable physics, and that's something that's much talked about and is really kind of an exciting idea. So if you look at what we've done so far, again, we've built this training data set, we trained a neural network, and of course, this requires, we learn by gradient descent, and we're only going to talk about gradient-based learning now. So this requires our physics, which is a neural network, to be differentiable, which is of course given because, that's how neural networks work. But now if we unroll this cycle here, we have physics, dynamics, and so forth, maybe hundreds of thousands of those. And you have your physics, which have some machine learning or neural network component in it, and you have other model parameters, model components that don't. Now the idea is, well, let's not only learn for like one time step. Let's now, compare the state after every time step, or maybe after after a few time steps. Compare this to, well, you could use a high resolution simulation, but you could also use observations. And essentially, let's learn through this entire chain of physics dynamics interactions. And this requires basically us to differentiate backwards through time through this entire chain of physics dynamics. So this, of course, requires all of your model components to be differentiable. And then, similar to maybe a recurrent neural net, you just go back in time, and you could imagine a situation where you have a weather forecast, and you check after one day, okay, what is my error here? And I'm basically differentiating backwards through my entire simulation to lower my error after one day. Now, the great thing about this is that you automatically look at the coupled system. You can compare to observations. You can. And so it's really kind of a neat solution. And it's a solution that's much talked about, not only in climate modeling, where actually this has not been really tried before, but in a lot of other studies. And I'm basically, again, I'm dumping a bunch of references here that I found interesting in that context. So again, if you're interested in those, you can go to my website to download the slides and look at these simulations. I want to show from this last paper here an example of this. So basically, this is looking at a 2D Navier-Stokes simulation with a tracer here, which represents smoke. And on the right, we can see the reference simulation. That's a high-resolution simulation. On the left, we see a low-resolution simulation. You can see that they look different. And then if we run this again, if I manage to do this, then in the middle here is a simulation where a correction term was learned using a neural network. And they used this approach of differentiating backwards through 128 time steps. And you can see that it looks a lot more realistic than the low resolution simulation without the correction term. So that's really cool, and it kind of works. And so that's awesome. But also, this is sort of one of the most complex examples of this approach that I've seen so far. And of course, that's orders of magnitude away from a real climate simulation, right? So there's a lot of work to be done. These, differentiating backwards is very computationally expensive. This is again a huge technical challenge, and I think also once you look at a climate simulation where you have thousands, if maybe not millions of time steps, you need to make sure that do the gradients still make sense. So there are a lot of unanswered questions, but this is, conceptually, and also particularly for smaller problems, a really, really interesting approach. Now, if you know a little bit about weather forecasting in particular, you might notice that this actually has quite a lot of resemblance to a method of data assimilation called 4D VAR. So in 4D VAR, typically people do not try to estimate model parameters, but they try to estimate, the initial state or the state of the atmosphere at a time that best matches observations. And to do so, they use a differentiable approach, manually building adjoint models. And so I don't understand the problem. I have to admit, I don't understand data assimilation, the problem good enough to really, so I know that there's some resemblance. I don't quite know in which ways they differ, in which ways, you could actually use some of the framework that we already have in place for weather forecasting to follow this approach. But there is some resemblance there. So this might be a really interesting avenue to approach. Okay, now, I'm just going to briefly talk about another option, and that's non-differentiable optimization. So this is the approach that's being proposed by this Climate Modeling Alliance. And so again, if you want to know what they're all about, the basic outline is laid out in this paper, and then the actual method that they're using is described in a lot of mathematical detail in this paper. And I'm going to just try to explain it in like 2 minutes in the next slide. So essentially the idea is you have a model with some parameters, and they're actually not looking at replacing model physics with neural networks. They're really just trying to find a way of systematically tuning their fewer these traditional parameters of your parameterizations in a way that's not manually tuning, but that's systematic and data driven. So you have your parameters that results into a climate simulation. So this is the global mean precipitation. You have some observations, and you have the difference between those, and you compute a loss function between those. And so their approach is basically based on an ensemble common inversion, where you run an ensemble of simulations, each with a perturbed set of parameters. These will, of course, all lead to their own loss. And then in a nutshell, you build a covariance matrix between the two, and you keep updating your parameters to lower the loss. And so with the idea that you come closer and closer to the true solution. So this is basically this in a nutshell. The advantage of this is, of course, doesn't require you to do any differentiable physics. It doesn't require you to build a differentiable climate model, which of course doesn't exist at the moment. And essentially, and there are, if your loss function is very smooth, then this might actually work quite well. And ensemble common approaches are used operationally in weather forecasting as well. So there is some precedent that this can work. And this is really a very interesting approach. Okay. Final slide, sort of a summary slide. So we talked about hybrid machine learning physics modeling, particularly in the context of climate modeling, because that's the only thing I know anything about. So let's state some facts. Neural networks are very efficient function approximators, which means that given enough data, they can do really well and probably better than a human at finding, a fast approximate solution to a given training data set. So there's theoretically a huge potential for speeding up or improving complex simulations. I would say that there exists a neural network that creates a better climate simulation. I'm sure it does. The question is just, how do you find it? Another fact is neural networks are only good at exactly what they're trained for. They're very good at what they're trained for. but we're currently not training them for what we actually want. We're training them for something else and then hoping that they'll do well on what we actually want to get out of our simulation. And that evidence has shown is not always the case. So if you just train a neural network offline and it does really well, and then you look at online skill, that does not have a lot of correlation. Now, all of these things are also true for random forests, for example, which are actually a popular choice as well for this research because they're more bounded than neural networks. Potential solutions. So basically, this coupled online learning approach that I was talking about is sort of a data augmentation approach. One of the key issues is, if you just train offline, is that the neural network only sees samples that are sampled from a simulation that, where the neural network has nothing to do with it. When it's running in its own simulation, it will be exposed to states in the phase space that it has never seen during training. So this coupled online learning approach is essentially a way of augmenting this data as you run in a coupled simulation. And then there are differentiable approaches and non-differentiable approaches that might actually solve the issue that we're learning, that we want to actually get better climate and weather simulations, that they actually optimize for what you want at the end. So this is basically it. I just want to advertise 2 more things. So I already mentioned, if you go to my website, this talk will be on there. There are also 2 blog posts that I wrote about, the first one about basically the issue that I talked about today. And then there's also one on Lorenz 96, which is a really popular toy model, but it's probably too easy because it doesn't actually exhibit any of the problems we're dealing with in the for real world problems. And then machine learning in weather and climate, it's very popular right now, and there's a lot of there are a lot of data sets, a lot of papers being published. But what we noticed is that there isn't a great place where you can just see and kind of, oh, what are like good and common data sets that are being used for AI research in weather and climate. And so we created a website, if you go to mldata.pangeo.io, which has a list of all sorts of data sets. So if you have a method and you're looking for a problem in weather and climate, a data set that you want to apply this method to, then this is a great place to look. And also, if you know of a data set that you're using or somebody else has been using that's not on there, then you can also add it. So with that, I would like to thank everyone. And I'm really looking forward to questions.
Thank you, Stephan. That's very interesting. I think we have 2 questions in the chat, so maybe we'll start with those. Mm-hmm. So somebody asked why you didn't use data simulation and if online learning actually solves the problem of running the expensive model in the first place.
Yeah, so 2 good questions. So I think to the first question, as I mentioned, there is a lot of similarity with data simulation, and sort of basically, both of these approaches, the ensemble Kalman inversion and also the differentiable optimization, which has a lot of overlap with 4D bar, they're basically ways of using data assimilation approaches to this problem. So yes, just nobody has really done it yet for optimizing neural networks, or has really successfully. I mean, people have been using data assimilation to optimize model parameters, but to my knowledge, all of these things are not operational because there are some, issues with it. So, but yeah, this is also a really interesting area of research. Then for the second part of the question, no, this does not solve the problem of online learning, does not solve the problem of running expensive simulation. But the issue is, of course, that the idea is that you run the expensive simulation for short time. So, to create a training data set, you run a short-term high resolution simulation. Here also, you run a, so in the end, let's say we want to create a 100-year climate simulation, you would do this coupled learning, hopefully for not that long. You would do it for maybe a year or so, or like a few times, a few weeks or something. So as I said, I don't really have a great answer how this would work in a real climate setup, but the idea would be that you don't have to run this coupled system for quite as long as you want to run your climate simulation for.
All right, thank you. The second question in the chat is from Rob Akers. He asks about catastrophic forgetting, which can happen if your data arrives in a stream. So that's, in this case, you're neural network is always biased towards the latest data. And if this solves,
that's absolutely a problem. As you can see here, like where are we in this sort of animation, you can see that like your neural network will basically wobble around the true solution. Yeah, so this is definitely something to keep in mind. Again, as I said, like we have not tested this system yet in like an actual climate simulation, so we don't really know, but this is definitely a worry, yeah. I think there's somebody raising a hand.
Yeah, just unmute if you want to ask a question.
I had a question. Thanks a lot for the presentation, Stephan. It was very interesting. I'm wondering about in the differential physics context, if you have a machine learning model embedded in your physical model, part of the physical model, and you say, okay, everything is differentiable, then you can optimize everything at once, basically. Yeah? You optimize your neural network. I think that's also what you want to do or what you're trying to do. But I'm still wondering, I know a couple of years ago, people were saying this, but they would say, this is just too expensive to do. And I'm wondering, is that now alleviated because you somehow, and how does the training look like? How does the loss landscape look like? And can you say a bit also about the stability? Do you have guarantees of stability when you have it embedded in your
So basically, I have no good answers to your questions. All of these are very good questions, and I don't have great answers. All of the concerns you raised, I think, are still concerns. I think we do have, I mean, as I said, like this approach is basically for a pure like differentiable learning approach. This is sort of one of the most complex things I've seen. Which is of course still not very complex. And so I don't really have a good answer to any of your questions. All of your concerns are totally valid concerns. And we of course, we have more and more computing power, and there are of course ways also to, like one thing you want to do is you basically, you don't want to just use autodiff, like you can use shortcuts to differentiate backwards through, advection or whatnot to make this problem more tractable. But yeah, absolutely a problem, huge computing expense. And yeah, to which degree this still works if you look at very nonlinear problems or problems where you differentiate back through a lot of time steps, I do not know.
All right, I think Richard has got another question.
Yeah, hi, thanks for the really nice presentation. I was wondering whether you consider it necessary to use such a complex function approximator as a neural network in these cases. I mean, clearly in the Lorenz model, that seems like overkill.
Oh yeah.
And even perhaps in the more complex models, I mean, you can alleviate a lot of the complexity of your optimization if you simplify your function approximation. Have you considered?
Yes.
Yeah.
So Lorenz, absolutely. Linear regression, totally enough to do quite well on Lorenz. I do think that if you look at like really, if you look at a complete cloud parameterization, like basically, let me just show the slide here. Something like this, where you're really just trying to pack like your complexity of like of all these nonlinear processes into an approximator, then I don't think that very simple techniques like linear models would really be sufficient, right? Because you also want to outperform these models, which are definitely nonlinear and quite complex as well. Yeah. So, and we also see that just like if we look at just offline skill, like just how well do these models represent our training data set, bigger models tend to perform better. So this is actually quite a complex problem. And so I don't think we can go too simple with our models.
Okay, thanks.
Shihu?
Yes.
Next.
Yeah, thanks for the talk. I have a question about the uncertainty that you mentioned at the beginning of the slides. You mentioned that a couple of models, they have different kind of uncertainty. So I wonder, what's your definition of uncertainty? Is that simply the difference between the predicted value and the ground truth that we observe during test?
So we don't have a ground truth of this value here. Like we don't actually know how much warmer it will get as we have more CO2 in the air, right? So this is what we want to know. Basically, what this is basically you run these simulations where you increase CO2, you see how much warmer it gets, and then the uncertainty is just like sort of the spread of all of the different models. So some models predict 2 degrees, some models predict almost 5 degrees, and ideally we would have all these models be closer together so we can be more certain what will really happen, but we don't have ground truth data to evaluate against, which is, I guess, one of the really big problems in climate modeling is that, you have a sample size of 0, 1 or something like that, and it makes it really difficult to actually know what's going to happen. So we don't have a ground truth. What we would like to, the goal of climate modeling is essentially to build models that are as realistic as possible. And the idea is that as they get more realistic, they would converge more closely to the unknown ground truth. But this hasn't really happened so far.
So does it mean that you have an ensemble of models and each one perhaps initialized in a different state, and then?
So these are all completely different models. Oh. So they all have different representations of clouds, and so so they all have like different cloud approximations and so forth. So different, but it's not clear which one's better, right? But they all do it in slightly different ways. So yeah, so you have a multi-model ensemble essentially.
I see. So essentially, the uncertainty here is just the variance of the predictions of different types of models. Okay, great. Thanks.
Thanks for the question.
We've got another question from Wouter and also a few new ones in the chat, I see. So maybe Wouter goes first.
Hello, sure. I wanted to ask if the model has any built-in understanding of time scales and spatial scales, like if there is a quiet region, does it use less computational power in some way to attack those problems?
You mean the neural network?
Yes.
No, it does not. I mean, the neural network is very fast compared to, it's just a bunch of matrix multiplication. So it's essentially quite fast compared to all the other model components. So we don't really need to worry about computational speed too much. But it is actually an interesting point about timescales and spatial scales. So, I haven't seen a model yet that actually has memory, and most models work in a single column. So not taking neighboring grid points to account, just like a single vertical column. So this is something that, might have to be explored.
Thank you.
So in the chat, Gijs van den Oort asks why you're not nudging the other way around, because that would perhaps allow.
So good question, and I was thinking about this for a long time actually. The reason why you're not nudging the other way around is because you don't want to really modify your low resolution simulation, because if you like the idea, again, this on the right side here is not the final step. It's another learning phase, but then eventually you want to run your hybrid model without supervision. So you need to make sure that, and so if you nudge the low resolution your hybrid simulation during this online training step, but then in the actual eventual simulation, you then don't nudge anymore, then again, you have the problem that you're basically learning on a different, slightly different attractor maybe than what you then actually want. So you really want to keep this hybrid simulation untouched so that it's in its natural habitat, essentially.
Can you hear me? Can I just comment on that? Because as I understand, neural networks develop biases according to the data that is fed to them, basically. So if you have initial biases and you nudge your high resolution towards this, well, maybe state with too low clouds or whatever, or too much climate feedback, etc. Aren't you worried that you basically are in a rabbit hole, basically. And
yeah, no, absolutely. I mean, whether this approach works depends on some assumptions, and one assumption is that this distance isn't too much, because then also the nudging isn't too much. So, and then you can assume that, you know, you're basically learning the true high resolution simulation, and you're not like contaminated by the nudging too much. So the nudging needs to be strong enough to keep these two the same, but not too strong so that it affects the high resolution simulation too seriously. So this is, like, as I said, like, this is basically this approach is not perfect. It just has some advantages that the reason why I came up with this is because, you know, essentially we could build this now. Whereas, you know, these differentiable models and stuff, like, you know, that I cannot just build a differentiable climate model right away. So there are some assumptions that I don't know if they would be fulfilled in a real simulation. And these are very good points, and I just don't have the answer. Also, I think you asked you asked the question about reanalysis data sets. This paper, the Wattmeyer et al., you want to look at that because they essentially learn a nudging towards reanalysis. So this is a really interesting paper. It still suffers from the problems that we talked about, but it's a different approach, and, you know, these results are really cool. So I think you want to look at this paper because they're doing maybe something along those lines.
Okay, we got one more question from Enrico. He asks, what is the status of end-to-end machine learning models in climate science?
Yeah, good point, good question. So end-to-end, you know, I guess means like you input your current state, you output a future state. I think climate modeling is not a good field for this, because the issue is that, as we talked about, we don't really have, like, if you really think about a climate simulation, we don't have any training data, right? We cannot just, like, we have good observations for maybe the last 100 years. We want to predict the next 100 years, which are going to be out of sample. So that doesn't really work. Now, of course, what you could do is you could say, okay, well, I'm just going to get rid of this entire thing. I'm just going to do like one time step completely with machine learning. And then I don't have to worry about all of these hybrid interactions. And so actually, this is something that that I've looked into, and a bunch of other people have looked into recently, mostly in terms of weather forecasting, because, you know, weather forecasting, you have a lot more training data. You can actually compare against observations. And this does kind of work. So actually, I was working on a benchmark data set called WeatherBench that tackles exactly that problem. And so you can maybe look at some of the papers from that. And but it turns out that it's going to be really hard to actually do better than physics-based modeling there, because again, we don't really have the training data that we need. We don't have enough training data at the high enough resolutions. So that is an interesting approach, but again, like, I think it's going to be hard to actually do better than a current weather or climate model with that approach. For longer term forecasting, if you think about like a shorter term problem of predicting precipitation for the next few hours, this approach of just doing like purely data driven might actually work quite well.
I think I see one more question in the chat from Gijs. He asks about ocean sea ice and vegetation feedbacks.
Again, very good question, and I don't have a good answer. like this is like a great concern, and I think like the general gist of it is that if we think about, you know, this basic approach of basically doing this for climate modeling, I think we're still very much in the beginning of figuring out how this could work. And so one thing I didn't really talk about is, like, here I mostly talked about, you know, building a new cloud parameterization with machine learning, one that's better than what we currently have. And that, I think, like, is really, really hard, and we need to do a lot of research still. Now, if you have an existing parameterization that's expensive but good, and you just want to speed that up, for example, that's a problem that's maybe a little bit easier, and there are some people looking into this for example, radiation parameterization and microphysics parameterizations, and that might actually be a lot more promising. You're not actually improving the model because you already have these parameterizations, you're just making it faster. That might be a more achievable goal in the near future.
All right, thank you. Any last questions maybe from people in the audience? I might have one question. So if you do online learning, you think the size of the neural network matters? If you have a very large network, if it has some sort of inertia that makes it harder to update on the fly?
Yeah, that is true. On the other hand, of course, when we talked about the sort of like forgetting problem, you might, maybe a larger neural network would be less prone to doing that, especially if you pick the learning rates correctly. Again, like, this is something you'd have to try out. I mean, as I only tried this out in a Lorenz model, and the neural network that I trained was pretty simple, I think. It was like, a few layers with a few dozen of neurons or something like that. I didn't really have a good way of testing them, but open research question, I would say.
All right. Well, thank you very much.
Yeah, thank you. Excellent questions. It was really great.
Yes, and I think I'll put the video up on YouTube if you don't mind.
Yeah, please do.
Yeah.
Cool. All right.
Oh, thank you very much.
Thank you. Okay, bye.
Bye-bye.